All right, as promised, we're going to do a lot of examples right now. They're just for practice. You really already have a lot of the ideas down about differential equations and solving them with the most basic technique we have, which is integration and get rid of plus c. But now putting it in practice sometimes can be a little intimidating. So I'm going to do 10 examples. We're going to do 10 word problems that come from a variety of textbooks or that I've kind of changed a little bit to fit our situation. They're going to go from the easiest to the hardest. If you're getting this, don't be afraid to skip a couple. Go on to the last ones. Those are going to be the most difficult ones. But if you stick through it, stick with me here, I think they'll help you make a lot of sense out of this. Just the way that you approach them, the way you think about them is important. Otherwise, even though the math isn't all that hard, get stuck on the simple stuff, like what is it even talking about? So we're going to go through about 10 of them. Let's start right now. So let's say you're sitting on the ground and you decide for some reason just to shoot a slingshot right above you. And then hopefully you move because you're not an idiot and you don't want to get hit in the face with a slingshot because that hurts. That's how I know. So anyway, you know that your slingshot shoots this little projectile upward, so positive, at 49 meters per second. What's the maximum height you're going to get out of that, assuming that you're on the ground? Well, we need a little bit more information than that. So we need to know what planet we're on. Now, we're going to assume that we're on planet Earth here. So assuming that, we know that acceleration is constant when we're talking about things flying. Acceleration is negative 9.8 meters per second or negative 32 feet per second squared on each of those cases. Well, then look at your problem. What are you dealing with, feet or meters? Since we're dealing with meters, we're going to take acceleration as a constant negative 9.8 meters per second squared. Also, we're assuming that we're sitting on the ground. So if we're on the ground, so we kind of launch it, maybe you're dug a little hole and you're under the ground. You launch it, so it's leaving the slingshot at 0 feet. Those are two really important pieces of information that we need to have to solve our problem here, but it's stuff that you're inferring. We're on planet Earth. Acceleration of gravity is negative 9.8 meters per second squared. We're using meters because we start with meters, and you're on the ground. Let's say that your height is 0. Let's start this. From the last couple videos, we know that acceleration is the second derivative of position. We're going to start taking integrals. So integral of acceleration. In all these cases, you're going to start with acceleration. So keep that in mind. Every time. Acceleration's first. Take an integral of that. So if we integrate our constant acceleration, we're going to get our velocity is negative 9.8 t plus c1. Now, we have an initial velocity. We know that this projectile is leaving our slingshot at 49 meters per second. That's something we can use. At time 0, we're going 49. So our velocity is 49 when our time is 0. And that lets us solve for our c1 just like before. So if we augment our equation with this, that's negative 9.8 t plus 49. That's our velocity function. Now starts thinking, okay, well wait a second. What's our maximum height? How in the world are we going to find that? Do we need position to find that? We do. But think about what happens when you shoot stuff up in the air. If you've ever done this, if you shoot something in the air, it's going to have positive velocity, and then it's going to have positive position, and it's going to reach a maximum height. It's going to come back down and have, I don't want to use that word. It's going to have a positive velocity and a negative velocity. So it's going to come up and it's going to come down. At the top, its velocity is 0. So if we want to find the maximum height that's attained by this, then we set this equal to 0. It's going to give us the time that we reached its max. So again, if that made sense to you, we shoot something up, it's going to have a positive velocity, it's going to stall out for the briefest of moments, it's going to have a negative velocity. At the very, very top, our velocity is 0. So think critical points. This is first derivative, critical points that equals 0. Same sort of idea. If we solve this, add 9.8t to both sides, divide by 9.8, we get 5. So 5 seconds. What that means to us is that our velocity is going to be 0 after 5 seconds. That's exactly what we did. Here's velocity, here's 0, 5 seconds. So we're going to reach the maximum distance away after 5 seconds. Now that's important information, but we need a position function to plug that into to figure out what our max height is. If we integrate this one more time, we're going to have that position. So our position function, when we integrate this, is going to be negative 4.9t squared. So we add 1 to the exponent divided by 2, plus 49t plus c2. Well, in order to figure out our max height, we need to figure out our initial position. Now, we were sitting on the ground, so we're assuming our height is 0 at time 0. So our c sub 2 is just going to be, it's going to be 0. Obviously, we're sitting on the ground. So our position function, how far away we are with respect to our time here, is negative 4.9 t squared plus 49t plus 0. There's nothing there. So here's our idea. We start with acceleration. We inferred that we're dealing with the Earth, so we have negative 9.8 meters per second, meters squared. Meters because we're given a unit of meters. We do an integral, we find velocity. That needs an initial velocity to figure out our c sub 1, which we have. But then we think about how a maximum height is going to be attained when our velocity is 0. When our velocity is 0. So that's 5 seconds away from when we shot it. So shoot, 1, 2, 3, 4, 5, reaches the peak, comes back down. So when we integrate one more time, we have our position, we use our initial position to get our equation, and now we can say, well, hey, our position, our maximum distance away happens after 5 seconds. Let's just plug in 5. So our position after 5 seconds, we know that's the maximum distance away. Let's just plug in 5. I've worked it out, maybe you can work it on your own. It's around 122.5 meters. So we sit on the ground, we shoot a slingshot. It has 49 meters per second as an initial velocity from a height of 0. It's going to take 5 seconds to reach the peak. Here's our position function, and we plug in those 5 seconds. That's the peak. That's how far away it is. I hope that makes sense. So let's keep on going to the next one. We're going to drop a brick. Obviously, that's what you do when you're 400 feet up. You just drop bricks off. It's bad. So, well, it'd be kind of fun to watch, though, wouldn't it? Like you sit on a canyon, just drop it, watch. I've done that when I was a little kid. See how long it takes to hit the ground. Well, let's figure that out without having to drop the brick, because you're probably not next to a canyon. So if we are going to drop a brick from a height of 400 feet, when is it going to hit the ground, and what speed will it hit the ground at? Well, what planet are we on? Probably on Earth. So let's pick acceleration to be constant, and let's look at our units. Our units are given in feet, so I don't want to be using negative 9.8. I want to be using negative 32, because that's a feet, and we're going to be dealing with feet per second. Our initial velocity, well, we're dropping it. So we're not throwing it. We're not throwing it up. Let's assume that our initial velocity is 0. These are all logical inferences we can make, but are very important. We also know that we're 400 feet up, and we're just dropping the brick. So our initial position is 400. This is basically how I try to start every single one of these problems. I figure out what we know from the word problem that we're given. So we know we're on Earth, negative 9.8 if we're dealing with meters, negative 32 if we're dealing with feet. Look for an initial velocity. A lot of times it's given to you, or if you're just dropping something, you can assume that's 0. So it's starting at 0. From the moment you drop it, it's 0, and then it's going to increase speed downward. What speed is it going to hit? Well, we're going to answer that later. And then our initial position is 400 feet up. We can infer that from the problem. Let's get started. Let's do an integral of acceleration to give us our velocity. So we know that we're going to get negative 32t plus c1, just some basic integration here, but we do know an initial velocity. We're dropping it. It's not starting with a throw or a down or up. So we know that at time 0, we have a velocity of 0. Hopefully you can see that your c1 is just going to be 0. At time equals 0, so that's gone, we get 0. c1 is 0. So let's rewrite this. Our velocity function is just negative 32t. That's cool. Now that we have our velocity, well, it's not really, it is asking us for a speed when it hits the ground, but we need to know a time that it hits the ground for us to find our speed. So it's sort of backwards of this problem. Here, we needed to find a position after a certain amount of time when the velocity was 0, when it reaches peak. Here, we need to find the position first to figure out how long it's going to take to hit the ground. Therefore, we can backtrack and plug in the speed. So it's a slightly different problem, which is why we're doing it, even though it seems similar. Let's find the position. Position is an integral of velocity. So we're just going to integrate, but we do know our initial position. At time of 0, we're at 400 feet. So if C2 is 400, we have a position function. Now, let's answer the two questions. So we start with 400 feet initial position. We dropped it. Velocity is 0 when we start. Acceleration, we're at planet Earth, negative 32 feet per second squared, because we are dealing with feet. We did our integral to get velocity. We had initial velocity 0, c1 0. Did another integral to get position. We have c2 is 400. That's our initial position. And now we think, when is it going to hit the ground? What's the t when our position is 0? So if we start from 400 feet up, the ground is at 0. So when we hit the ground, it's going to be a height of 0. We need to solve for t when our height is 0. So a variety of ways you can do it. You can try to factor, you can add 16t squared, divide by 16, take a square root. That's what I would do. So if we do that, add 16t squared to both sides, divide by 16, excuse me, and take a square root. You don't need the negative. We're dealing with time. Real life, time doesn't go backwards. It would be kind of cool if you threw bricks and went back in time, but that's not the case, unfortunately. The only time is the one dimension that you can't go backwards on. It's called regrets. No regrets. Not even Leonard. So here we're going to divide by 16, take a square root. We just get the square root of 400 over 16. If I did my math right, that looks like it's... Is that also 5? Probably. Let's see, 400 divided by 16 would be 25. Okay, so 5. Just to let you know, not everything in cool happens after 5 seconds. I know it looks that way. It doesn't. So 5 seconds is what it's going to take for this brick to hit the ground. So we're at 400 feet. We just drop it. We don't throw it. We don't throw it. We just drop it. Initial velocity is 0. It's going to hit the ground after 5 seconds. So we answered question 1. When does it hit the ground? 5 seconds after we drop it. How fast is it going, or what's the speed? we have a velocity function right there. It's just negative 32 times whatever time you want. So when it's hitting the ground, it's at 5 seconds after we've dropped it. So if we want to figure out the speed when it's hitting the ground, it's the speed after 5 seconds exactly. Speed has the idea of being signless. So even though the velocity would be negative, whatever that's going to be, looks like 160. So negative 160 feet per second, a speed is the absolute value of velocity. So the speed is 160 feet per second. Of course, we know it's dropping, so it'd be negative as far as velocity, but positive for 160. So that's the idea with pretty much all of these. Try to find out the information that you can infer from the problem. Don't make stuff up, though, okay? Find the information that you can infer. Use the appropriate units for acceleration. Do an integral. See if you have initial velocity. See what question they're asking. Are they asking for a maximum, or when a maximum height occurs, or maximum height? You're going to want to find out when the velocity is 0. Are they asking when it hits the ground? You're going to want to find out when the position is 0. And then typically we go one of two directions. Fill in a velocity first to find a position, or find a position first to fill out a velocity. I'm going to put a few more up there. We have like 8 more problems to do. So hang on, we'll be right back. So our next 2 examples. Let's talk about a car. Car's going 100 kilometers an hour or 60 miles an hour. That's the same thing there. It brakes at a constant deceleration of 10 meters per second squared. How far is the car going to go? One thing that's really important, and where a lot of people just get mixed up or don't know why their numbers aren't coming out, match your units. That's a big deal for examples like this. So if something's in kilometers per hour, yet you have an acceleration of meters per second, you're going to want to find meters per second. Meters per second squared, you're going to want to find meters per second. So kilometers per hour and meters per second don't really go together really nicely unless you convert one of them. We typically convert the kilometers to hours to meters per second. So let's convert this down to the acceleration units of that's meters per second squared. Meters per second is going to work great for us. So 100 kilometers per hour remember, you want units to cancel, so put your hour as across a fraction, numerator, denominator, across a fraction. 1 hour is the same thing as 60 minutes. One minute's the same as 60 seconds. So if we get this, at least we'll have kilometers per second. Well, we also know that there's 1,000 meters in a kilometer. And if we do that, we remember kilometers, we're going to have meters as the unit on top, seconds as the unit on the bottom. So basically multiply 100 times 1,000, divide by 60 squared. And we're going to get, looks like I got 27.8 meters per second. So our car, or whatever we're doing, is going 100 kilometers per hour. That's 27.8 meters per second. And then we slam on the brakes. And we're going to assume that we have a constant deceleration of 9.8 meters per second squared. Deceleration is negative acceleration. So it's like falling to the earth or something. We're not accelerating, we're decelerating. So our acceleration is a constant negative 10 meters per second squared. Let's see if we can run with that. Oh, and our position. What's our initial position? Well, we're looking for how far do you go? How far do you go from what? Well, call where you start braking 0. Call that your initial position. If we're only concerned with how far we're traveling from that point, let's assume that when we start braking, we're at some place in the ground we call 0. We're going to measure from that spot. So our initial position is just 0. let's see what we can do. Let's start by taking the integral of acceleration. We know that velocity is an integral of acceleration. So in our case, our velocity is negative 10t plus c1. We also know that we have an initial velocity. It's going to let us get rid of the arbitrary constant. When our time is 0, our velocity is 27.8 meters per second. That's going to be 0. So c1 equals 27.8 meters per second. No problem. Let's put that back in there. So our velocity function is now negative 10t plus 27.8. That's looking good so far. Excuse me. Now, we're also looking for how far we go before we stop. If you remember from like 5 minutes ago, I said that a lot of times when we want to find a maximum height, what we do is we find out when the velocity is 0. Well, if we want to find out how far we are traveling, we're going to want to find out when our velocity is 0. So we're going to find that out first. When's our velocity 0, then find our position, and then plug in that time to figure out how far we're going. You see, our position is never going to be 0 again. We started at 0, we're going past it. So it's not appropriate to solve for position first and set it equal to 0. That does nothing. You're going to get the time is 0. That doesn't... Yeah, okay, we know we were at 0 when we went past that and started braking. What we're concerned about is when's the velocity 0? When have we stopped moving? Because if we find out when that is, then we find our position function. We can plug in that time and figure out how much distance has been traversed. That's the idea. So let's figure out when we hit a velocity of 0. So when velocity is 0, that's a horrible... looks bad. Well, that's when our velocity is 0. Looks like if we add 10t, divide by 10, we just get about 2.8 seconds. So again, we knew our deceleration. That's what that said, constant deceleration. We know that if we change this to meters per second, it's going to work a lot better. So we find our integral of acceleration gives us velocity, but we're concerned with how far we're going when we stop. Well, we need to know when we stop to find out how far we're going when we stop. We stop when the velocity is 0. That's after 2.78 seconds. Now when we find our position function and we plug in 2.78 seconds, we'll find the distance that it takes us to stop with the vehicle. I hope that's making sense. Sometimes you have to figure out something first in here to figure out the position that you want. So let's go. Let's find our position now. Position is an integral of velocity. So in our case, we're going to have this negative 5t squared plus 27.8t plus c2. Now, we have an initial position. We said that we're going along and we're gonna stop at this one point in the road. So that's our time 0 and that's our position 0. And how far we go from there, we're just measuring that distance. How long it takes us to get there is the time that we just found. It says it's going to take us 2.78 seconds to go from 100 kilometers an hour, or 27.8 meters per second, to 0. That's how much time is going to pass. But as far as our position is concerned, we know our initial position was 0, so we can just make that 0. You can think about it. 0 goes here, 0 goes here. Your C2 is going to be 0. Start with acceleration or deceleration. It's negative. Take an integral, use our initial velocity to figure out our arbitrary constant, and then if we want to find out a maximum distance of travel, that's usually done by setting your velocity equal to 0, finding a time it takes you to stop, and then plugging that time into the position that you find later. So now we can plug in 2.78. We plug it in here. I did it. You can check it on your own. I got about 38.6 meters. So we slam on our brakes, we have constant deceleration, and it's going to take us 2.78 seconds to stop. And as that 2.78 seconds passes, we're going to have gone 38.6 meters. So is this important information to know? Well, of course it is. It's important if you want to judge how well you can stop, how well your vehicle stops, whether it's a car, a truck, or anything, doesn't matter, or a plane even. So we'll want to know what our initial velocity is, we'll want to know what our deceleration is, we'll want to know all these things. Now, we talked a little bit at the beginning of this course about modeling and how there's a big trade-off between a perfect representation of a situation and ease of doing the math. This is very stripped down. We don't have coefficients of friction in here, we don't have wind resistance, we're kind of stripping this way, way, way down. But this is how we start. Okay, the next one. Let's assume you got a paintball gun, because I love paintball, and so you're going to kind of impress your friends. Don't do this because wind resistance is going to mess all this up. But if you stood on a 20-meter high building, you just go, check this out, guys, and then you count. You say, yeah, when's it's going to hit the top of the building after this far. So after like however many seconds, I'm just going whoop, and it's going to go right by me and hit the ground. It's going to be awesome. It's so cool. You're probably getting nailed right in the face. It's going to hurt. Been hit in the face before. So let's assume that you do that though, because you're a daredevil and you want to live on the edge of a building that's 20 meters high, and you shoot your paintball gun up at 300 meters per second. That's about right. That's about 300 feet per second. Well, our units match up. That looks good. So 20 meters, 100 meters per second. We're going to find our maximum height. Think about right now. Your maximum height is going to be the height when your velocity is 0. So we're going to do the same kind of thing here. We're going to find out when our velocity is 0. Okay, that's going to give us the time when we achieve our peak, our maximum. We're going to plug that into the position. When it's going to be at the top of the building, once we find our position, we'll set it equal to the height of the top of the building. That's 20. Solve for the time. And when it hits the ground. So we'll set this equal to 0 and figure out the time when we hit the ground. So same idea, but to figure out our maximum height here, we're going to have to find the velocity of when the velocity equals 0 first. Let's start with our acceleration. If we're on planet Earth, our acceleration is, we don't want to be using feet. That's not the idea here. We're using meters, so negative 9.8. Our initial velocity, we have one. We're shooting this upwards. So we're up here on this little ledge and we're going, and you're going to be right here and you're going to go, whoop, move your head out of the way. It's going to hit the ground and go splat. At least that's what you want. So our initial velocity is 100, positive 100, because you're shooting this up, meters per second. Our initial position, you're at the top of the building. So you're 20 meters up, positive. That's all we really need. Let's go ahead and let's do an integral of acceleration. To give ourselves some velocity. Now we have that initial velocity. We know that our initial velocity is 100 meters per second. So let's plug that in. If we are going 100 meters per second at a time of 0, our C1 is our initial velocity. I told you that with polynomials, with constants, it's really easy because your C1 is 99% of the time, it's 100% of the time. It's going to be your initial velocity, and your C2 is going to be your initial position. So our velocity function here is negative 9.8t plus 100. Now, we want to find out what the maximum height is. Maximum height occurs when our velocity is 0. Stops, stalls out, falls back down. So we want to know that. So when our velocity is 0 is the time it takes for us to achieve our maximum. Well, that's going to be, let's see, add 9.8t, divide 100 by 9.8. Looks like we get about 10.2 seconds. So we know it's going to take 10.2 seconds for us to shoot this little paintball up and it achieve its max, its peak value. That's going to be important when we find out our position. So let's keep on going. Our position function is just the integral of whatever velocity you just found. So we're going to have negative 9.8t, we add 1 to the exponent, divide by 2, that's negative 4.9t squared, plus 100t, plus c2. Now, I just mentioned this, but that was a polynomial, and when you're dealing with polynomials, you're integrating, you're just kind of manipulating the coefficients and the exponent of your variables. So when you plug in 0, they're all going to disappear. That means your c2 is going to be your initial position. Our c2 is going to be 20. Now that gives us something that we can work with. So there's 3 questions that we're going to answer right now. The first question is, well, what's the max? What's our peak, max height? Since we were smart about it, we knew that the maximum height is achieved when you change from a positive velocity to a negative velocity. That's when the velocity is 0. Think critical point, think first derivative, because that's what we're dealing with. That happens after 10.2 seconds. So if we want to find out what our maximum height is, what our maximum position away is going to be, it happens after 10.2 seconds. Just plug in 10.2. So max, plug in 10.2. I'm going to assume that you can do that. Take this number, plug it in here, and you should get looks like I got 530.2 meters. Now the next questions are when questions. When is it going to hit the top of the building? Well, past the top of the building. And when is it going to hit the ground? Those are position ideas, but solving for time. So when is it going to reach the top of the building again? That's when is the position going to be 20? When is it going to equal the height of the building? So let's call this number 2 and number 3. For number 2, all we really want to know is what's the time when our position is 20? If you see this, man, you're asking, here's my position function, the time it takes to be at positions. We want a position of 20 meters up. Subtract the 20 from both sides, you can factor out your t. So I'm going to let you do that. You should be able to do that on your own, at least at this level. Subtract 20 from both sides, factor out t. You'll have time is 0. Obviously, when you start, you're at the height of the building. Or time is factored, look like this. Set both those equal to 0. So time is 0, yeah, you're at the height of the building. Or just take 100 divided by 4.9, and you're going to get the time that it takes to reach the top of that building. I got that it's 20.41 seconds. Now, when does it hit the ground? Things hit the ground when their height is 0. So here's our height, our position, and here's the time it takes to get to that position. For number 3, we want our height to be 0. Use the quadratic formula. Use difference completing the squares. I don't think you can factor it. If you can, it's not easy. I think you have to have quadratic formula. So when I did that, I got 20.61 seconds. So just 0.2 seconds after you pass the building. So we're setting up with the knowledge that we can infer from the problems. We're making sure our units match up. That's important. So translate them if you have to. Do your conversions. Make sure you use an appropriate acceleration of gravity if you're dealing with that. So if you're given meters, use negative 9.8. Given feet, use feet per second. Then what we're doing is figuring out if we want to find a max height, a maximum how far we travel. Typically, it's set the velocity equal to 0, solve for time, plug it in later. If it's a when we hit the ground, when we reach a certain spot, how far we go, like braking wise, that's dealing with position, and that's using the time for when your velocity equals 0 in that position function, or setting the position function equal to some value. Again, we have a few more examples. All right, here's another 2. So you're standing at the top of a building and you want to show all your friends just how muy fuerte you are. So you're going to toss a watermelon. That's what WM is. You're going to toss a watermelon. It's right there. I can throw this thing. So you stand up there and throw up the watermelon at 10 meters per second. And it's going to go up, it's going to come down, and it's going to splat. Waste a good watermelon, but it probably would be pretty cool to see. So you throw a watermelon up on the top of this building at 10 meters per second. It's going to hit the ground at 60 meters per second. The question is, how tall is the building? Let's start with what we know. So think right now, if you haven't done this, think right now, think about what you know. Can you put up an initial position? Can you put up an initial velocity? Can you put up acceleration? Can you do it in the right units? Let's start with acceleration. Right now, in your mind, you should be thinking, I'm dealing with negative 9.8 because we're on Earth, assumedly. That's the only place we know that there are buildings. And this thing is going to be dropping. So negative 9.8 meters per second. So we're matching up units as meters per second squared or meters per second. Initial velocity, it's given to us. We know that we're throwing this up. Now, positive, negative is important. If we had taken this watermelon and thrown it down, we'd have negative 60 meters per second, or sorry, negative 10 meters per second. Now we know that we're throwing this up at positive 10 meters per second. Initial position, do you have that? Do you have an initial position? Well, I mean, if we did, our problem would be answered. Because if we had an initial position, we would know how tall the building is. We don't know that. So we're literally looking for our initial position. Something we don't know. Well, dealing with what we do know, let's start with plugging all this stuff in. Oh, you know what? I think I did this wrong. I think I told you just right now that we're throwing the watermelon up. I didn't put negative on here on my notes. So let's assume we're throwing it down. So had we been throwing this thing up into the air, I misread my problem here. If we'd thrown this up into the air, we would have positive 10 meters per second. That's away from the ground. So if our ground is our 0 level, that would be away from that, so positive. Now we're not doing that. We're taking it and we're throwing it. I mean, who throws watermelons up anyway? You're not going to do that. Just throw it down. So we're going to throw this down at 10 meters per second. So that's negative 10 meters per second. Let's start with this. Let's start with our acceleration. Let's see if we can use our initial velocity, come up with a velocity equation here. Well, we know that our initial velocity is negative 10. Hopefully you can see that our C1 is going to be negative 10. At a time of 0, we have negative 10. So our velocity function is negative 9.8 t minus 10. Now, here's an interesting thought. We don't really care about the maximum height here, how far it's up. What we care about is how tall the building is. Well, if we have how tall the building is and we're throwing something down from the top of it, we know the time, we can find the time it takes to go from where you threw it to where you hit the ground. Furthermore, we know that we hit the ground at 60 meters per second. That's a velocity. So if we hit the ground at 60 meters per second, we can find the time it takes to to achieve that speed or that velocity. If we can find the time it takes to achieve that velocity is when we hit the ground, and that time would be the exact same amount of time it takes for us to throw the watermelon down there. So we start with our acceleration, we do an integral to find velocity, we use our initial velocity, sure, but this time of when we hit 60 meters per second is precisely the time it takes for that watermelon to hit the ground. So let's set this equal to 60, the velocity when we hit the ground, and solve for time, the time it takes to achieve that velocity when we hit the ground. So, since our velocity is downward, you need to make sure that this 60 meters per second when it's hitting the ground is not positive. It's not bouncing up. The velocity is making our position go downward. It's a negative velocity. So negative 60 equals negative 9.8 t minus 10. Let's go ahead, let's add 10. Divide by negative 9.8. I get 5.1. 5.1 seconds. So here's what that means. What that means is it is going to take 5.1 seconds for our watermelon to reach a velocity of negative 60 meters per second. Now, we know that when it reaches the velocity of negative 60 meters per second, it's hitting the ground. So that's the time it takes to hit the ground. Let's go ahead and find the position function and then backtrack. If we know it takes 5.1 seconds to hit the ground, we should be able to use that to figure out our building, or the height of our building. So integral of our velocity yet we don't know an initial velocity. What we know is that it takes 5.1 seconds to hit the ground. So if it takes 5.1 seconds for us to hit the ground, let's plug in 5.1 for our time, and let's put hitting the ground, or a position of 0 for our position. So 0 is achieved, a 0 position is achieved when we have 5.1 seconds of time that has gone on. That will allow us to solve for that C2. So we know that a position of 5.1 seconds is 0. That's what we know. Let's use that. So 0, so after 5.1 seconds. If we square 5.1, multiply by negative 4.9, multiply 5.1 times 10, subtract it, C sub 2 is going to equal 178.4 meters. So if you want to look back at your position function, C sub 2 is 178.4, but we know that's initial position. So if you just wanted to find out time of 0, okay, sure. Plug in time of 0 here, you're going to get C2. C sub 2 is 178.4 meters. That's how tall this building is. So you sit on top of this building, up down to watermelon at negative 10 meters per second. It's going to hit the ground at 60 meters per second. We use that fact to find a time when it achieves 60 meters per second downward. We went backwards from position, plugged in the fact that it's hitting the ground, that's 0, at 5.1 seconds, that's time, and that let us solve for C sub 2, which is our initial position. That's kind of cool. So we know how tall that building is now. Okay, next one. Let's suppose you're in a truck and you're traveling 60 miles an hour. So I'm going to do the conversion for you right now. That's 88 feet per second. So we're going 88 feet per second. And you start to slide under constant deceleration. So you press on the brakes, you're on some sort of surface that maybe was slippery or you just lose traction. You start to skid. Let's assume that we're under constant deceleration and you skid a total of 176 feet. You could modify this problem and say, okay, you applied your brakes and it took you 176 feet to actually stop. That's fine. There's lots of different ways to think about this. How much time did it take for you to stop? And what is the deceleration? This is a weird problem. This is where things start to get a little bit trickier because you're not given that acceleration or deceleration. You're given that it's constant, but you don't know what that is. We're going to try to solve for that. So the first thing we're going to start with is how much we know. So like what do we know here? Well, we know that acceleration is constant. Let's call it c sub 1. The next thing we know, let's assume that our initial position is 0. We start at 0 because we're trying to figure out from that point we slid 176 feet. Let's just assume that we start at 0. Now, the next thing, we don't actually have a, oh, we do have initial velocity. Our initial velocity is 88 feet per second from that point. So we're treating that as positive. We're going away from our 0 spot. We're not going towards it, we're going away from it. So that's going to be positive. Think about sliding upward, if you will. So our initial velocity is 88 feet per second. So we thought about, we go, okay, we have constant deceleration, we don't know what that is, it's part of our question. We know that we slid 176 feet from somewhere, so that was a total distance. Let's assume that we started at 0, that's when we applied our brakes. And we know that, well, right when we applied our brakes, we were going 88 feet per second. Hope this is all making sense to you right now. Now, let's slow down a bit, and let's work from this, because this really gets a lot of people. So constant, how am I going to find that? Well, we're going to have to make it to the very end before we find that. So you're going to have a C1 floating on pretty much the whole problem. Let's just start taking integrals. So we know that our velocity is going to be the integral of our acceleration, whatever that is. In this case, the constant, it's just C sub 1. So whatever that constant is, we'd add a t to it. And then we would get another constant, plus c sub 2. All right, well, we do have an initial velocity, don't we? So initial velocity is 88 feet per second. That occurs at time 0. So when we first start our situation, we're going 88 feet per second. At time 0, we're 88. So 88 feet per second at time 0, that actually lets us solve for our second arbitrary constant. That's kind of cool. So even though we don't know C1, we can still use our knowledge to figure out the initial velocity, or at least put that into our problem. So our velocity right now is C sub 1 t plus 88. It's looking okay. Now, one thing I'm going to show you what to do here is this. We're going to want to figure out the time it takes for us to stop. So in all the problems that we have done so far, where it says how far have you skid, well, we found out the time when we hit a velocity of 0. Now, this is a how far you have skid problem. We're still going to want to find the time when our velocity is 0. So this is going to look a little weird to you, but we have a velocity function. We're going to want to find out how much time it took for us to skid. Okay, that translates to you skid 176 feet. Find out how much time it took you to do that. But when you end there, your velocity should be 0. You should have stopped at the end of your skid. you stop there. So we want to find the time when our velocity is 0. Same idea in reverse. Before we said, okay, what's the time it took you to hit a velocity of 0? This much time. And now go backwards a little later and use that in your position function. Now we're kind of a little bit different. This is saying, you slid 176 feet. Great. All right, that's a position idea. How much time does it take you to get there? Well, that's going to happen when your velocity hits 0 still. So when the velocity is 0, let's solve for the time. So time is our when. If we subtract 88 and divide by c sub 1, whenever we find c sub 1, we're going to be able to find out the time that we skid for, or decelerated for, or came to a stop in. So we're going to find that later, but this is important. We need to understand that the time it's going to take us for us to accomplish this slide is 88 divided by whatever that C1 happens to be. Now, let's continue. So we're going to take our velocity, we're going to find our position, just like we did before. Before we said, what's the maximum peak here? Well, we found the time it took velocity-wise, and we plugged that in. That's the same thing we're going to do. We're going to find our position function. We found the time it takes for us to slide this. We're going to plug that in. It's going to be a little strange, but this is the idea behind it, is that we're finding the time it takes to do something, plugging it into the position, but now this time we actually have the position, so we'll be able to work backwards. So let's do one more integral. If we start integrating our velocity, we'll find our position. We know that our position function, this would be, well, c sub 1 over 2 t squared. Take 1, add 1, divide by 2. Then 88t. We've already used up a c2. Even though we found it, you really shouldn't put c2 again. Use c3 for your initial position. I'm going to pause right here because at this point, students, sometimes they go, what are you doing? Let's just go a little bit slowly. Let's think through this. Here's what's going on. You're in a vehicle. It doesn't matter what it is. You're going 88 feet per second or 60 miles an hour. You hit the brake. You slide or you stop in 176 feet. So we know that at the end of 176 feet, our velocity is 0. And you're assuming your acceleration is constant. Deceleration is constant. We start there. We know that our position, we're going to think of that as 0. It took us 176 feet from that spot to stop. Cool. Then our position initially is 0. We're also traveling 88 feet per second in a direction away from that. So that's a positive velocity. If we start taking an integral, yeah, we don't know what C1 is, but we do know that at the end of our slide, our velocity should be 0. So it doesn't matter what this is. Our velocity is 0 at the end of it. That's going to be this time. So 0 equals c sub 1t plus 88. If we solve for t, I don't know C1, but when I find it out, I'm going to be able to plug it in and figure out how long it took me to slide or to complete that skid. So we keep on going. We just don't know C1 yet. But we do know that when we take an integral of velocity and we get our position, we have a C1 in there. We also have an initial position that lets us solve for c sub 3, our last constant. So we know that if I plug in 0 for t, this is gone. Notice, this is, I don't care what C1 is, this is gone, that's 0. This is gone, that's gone. We would get c sub 3 equals 0. C3 is 0. Oh, that's funny. C3B0? C3PO? I just had to throw it in there. That's going to be 0. Plus 0. This is our position function based on whatever our acceleration is. Now, here's the magic part about it. Sure, we didn't know acceleration, we did know initial position, we did know initial velocity, we were able to use that to find C sub 2, that was our initial velocity, and C sub 3, that's our initial position. But we do know one more thing. We knew that the time it takes us for us to complete this skid, the time for us to take that it takes to get from a velocity of 88 to a velocity of 0. So when our velocity is 0 is 88 over C sub 1. But we have one more piece of information. When that happens, we will have slid 176 feet. Our position will be 176 when our t is 88 over C1. We can use that to solve for C1. So x of 88 over C1 is 176 feet. After this time, we'll have gone that far. It's gonna look bad. Oh man, I wish you guys were my real students. You would have stopped me like 20 minutes ago when I did this. Did you notice like the small mistake I made? It was a while back. It didn't affect any of this stuff, but it will now. I subtracted and I did not show that. So that would be negative, 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 and negative. I hope you're paying attention to those little things. When I do this math, I make mistakes. I don't ever really edit them out, so every mistake I make you guys see. But that's why I'm constantly checking. So I'm always going back, going, oh, sine. What's my sign here? And I noticed that it looked a little funny, and then I remembered that I subtracted, but I did it in my head too fast. And you will do that too. It happens to me. It's going to happen to you too. You do the math too fast, you're off by a sign. It's typically what happens when you're doing your head. So I subtracted 88 divided by C sub 1. That should be negative. I have negative here. None of this should have changed. That didn't change. But when I plug it in, I have a negative and a negative. So, again, to get us back on track here, I know that it takes us that much time to stop. This is how far we've gone when we stopped. Let's just plug in how much time has progressed or has taken place. Well, if we square C sub 1 and we have C sub 1 here, then what this works out to be, I'm going to have to erase this stuff. We'll have 176 equals C sub 1 over 2 times negative 88 squared. Oh, man. Well, I don't have that down. What I have down is if I take 88, I square it, and I divide by 2, we get 3872. So I'm squaring negative 88, it's going to be a big number, divide by 2, it's going to be 3,872 over C1 squared. This is going to get rid of that, so you're going to have C sub 1 on the bottom. Minus, I guess I did have 88 squared, it's 7744 over C sub 1. So 7744 divided by 2, should be that number, looks like it is. This multiplied together is minus 7744, and you have a common denominator now, C sub 1. That's pretty cool. So 176 equals, make one fraction, negative 388.72 over C sub 1. With fractions like this, we can just invert these two things. And we get negative 22. We have just answered the second question. So we are decelerating at negative 22 feet per second squared. That's pretty cool. If we plug it into this, we get how long it takes to skid. So after all this is said and done, you had to wait to the very, very, very end before you figured out C1. C sub 1 was our deceleration. We're decelerating at negative 22 feet per second squared. If we plug that into their time, it took us 4 seconds to slide. I hope this is making sense. I have a few more problems. I'll come back in just a second. Hope you're ready for another 2 examples. So let's go on this one. We're on a certain planet, and we're going to use this for both of these examples here. And we drop a rock, because that's obviously what you do on strange planets. You just drop rocks. And so we're dropping a rock from 20 feet, and we know that it takes 2 seconds to hit the ground. How long would it take from 200 feet, and what speed would it be going when it hits the ground? So let's start with what we know. Now, we're on a different planet, so we can't assume that gravity is negative 32 feet per second squared, but we hopefully can assume it's constant. Now, we also know that we're dropping the rock. We're not throwing the rock. We're not throwing it up or down. So our initial velocity is also 0. Hopefully you're catching this. This is important to get down. Finally, we have 2 other pieces of information. Not only are we dropping the rock from 20 feet, so our initial position is 20 feet for our setup here, it also takes 2 seconds to hit the ground. So it takes 2 seconds to have a position of 0. Those are 2 pieces of information. So constant, sure. Velocity 0, obviously. Initial position is 20 feet. But we also know that after 2 seconds, so our position after 2 seconds is 0 when we drop the rock from 20 feet. That's a big deal. Let's see where we can go from there. We're going to start with acceleration like always. We're going to integrate to get velocity. We'll see if we can use our initial velocity to get rid of our arbitrary constant. We'll integrate again for position, and then we'll see what happens with this whole setup. We're still going to have a C sub 1 in there. Our idea is to get rid of C sub 1. So our velocity is going to be the integral of our acceleration. Velocity, therefore, just going to be C sub 1 t plus C sub 2. We got to, C sub 2, that's fine. Now, we know our initial velocity is 0, so when time is 0, we have a velocity of 0. You should be able to see that C sub 2 is 0 right now. So our velocity function is simply C sub 1 t. That's pretty easy. Now let's find our position. A position function is always an integral of velocity. So that's going to give us 1/2 C sub 1 t squared plus C sub 3. I've already used up C sub 2. I can't use that again. So add 1 to the exponent, divide, and then add your other constant. So our position function C1 over 2 t squared plus C3. But we have an initial position. We know that we start from 20 feet. So we can go ahead and find our C sub 3 here. So at time of 0, that zeroes this whole thing out, we have 20 feet. We need that. Now comes the last piece, and the piece that lets us solve for our C sub 1, so our acceleration. We know that it takes 2 seconds for us to drop from 20 feet, where we start, to a height of 0. So 2 seconds gives us a height of 0. That's big. So we know that x is 0 when t is 2. From a height of 20 feet. So all this is now working together. Well, if we just do a little bit of math on this, we know that 0 would equal, that's 4 divided by 2 is 2, 2c1 plus 20. Subtract the 20, divide by 2. C1 equals negative 10. Let's plug that back into our position function. So now that we plug it back in here, right to where we started, right to where we just left off, we'd have negative 10 over 2. That's negative 5. T squared plus 20. This would be the position function if we started from a height of 20 feet. Now, what we're concerned about is how long would it take for us to hit the ground if we start from a height of 200 feet? This isn't going to change. Our acceleration is constant. That's what that says. So our acceleration is negative 10 feet per second squared on this planet. So when we get there, and it's like, oh, how? This particular planet, our acceleration, our acceleration here, the effect of gravity is negative 10 feet per second squared. We're going to use that over there. So keep that in mind. Our position function is, of course, half that t squared plus 20. Now, we want to find 200 feet. Well, what's going to change? Is that going to change? No. We're dropping the rock. Is the velocity going to change? No, just the position. So from 200 feet, the only thing that changes here is that we tack a 0 on, because now we're dropping the rock from 200 feet. So let's go ahead and find out when we would hit the ground. Hitting the ground is a height of 0. That's after t seconds. So 0 would equal negative 5t squared plus 200. I'd add 5t squared divided by 5. You're going to get the square root of 40 or 2 root 10. Again, we don't take negatives. You don't go back in time even on strange planets. So we have 2 root 10 seconds. That's how long it's going to take for us to drop this rock from 200 feet and hit the ground. How fast it's going, what its speed is, well, we're going to need a velocity function for that. Fortunately, we have one. It's right back up here. So velocity is c sub 1 times however much time you're taking. Well, we know c sub 1 is negative 10. So if we just plug that back in, velocity is negative 10t. We got c sub 1, that's negative 10t. We plug in our time. Velocity of 2 root 10 seconds. That's about, looks like 63¼ feet per second. So we didn't know acceleration, we knew it was constant, but we're still able to get down here. The key on doing these things is find out where you can use all of your information, and if you don't know acceleration, you're always looking to figure out where that's coming from. Typically, you have to make it all the way down to a position function. So that thing hangs on all through velocity, all through position. Figure out your arbitrary constants with initial velocities and initial positions if you can. But then all the way down here, when we finally get to use our position function, when we know something else about it, we know it took 2 seconds to hit the ground. Well, that's a solve for c sub 1. Then we can backtrack. Then we can say, okay, I now know c sub 1. Let's plug it into my position. Now I can use it to figure out how long it's going to take for me to hit the ground from a different height. 200 feet, okay, it's going to take square root of 40 or 2 root 10 seconds. Then I can say, backtrack even further. Our velocity is, hey, I know my c sub 1. Our velocity is negative 10t, whatever that is. We now know that that's 2 root 10 seconds. It's going to be 2 root 10 seconds for us to drop from 200 feet to 0, and we're going to be going 63.25 feet per second when we hit the ground on this particular planet. I hope that makes sense. There's a lot going on here, but I'm hoping it's becoming easier. I'm hoping you're understanding, okay, this isn't such a big deal. I can wait till later and then figure out, use some information that I'm given somewhere to figure out what that constant acceleration is, and then we're good to go. So let's assume that you can throw a rock 144 feet upwards on Earth. That's a long way. How high could you throw it on this planet? This obviously has less gravity because our gravity is negative 32 feet per second squared. This is negative 10 feet per second squared. That's what that C1 was. Remember where it came from. That's our acceleration here. So let's write that down. I know that our acceleration is negative 10 feet per second squared as far as our planet's concerned. So we're going to keep that in the back of our head. I'm going to put this in a little bubble. But what we really need to know is on our planet, what's your initial velocity? That's the only thing we really need to know because, well, we know how high it goes on our planet, that we're going to backtrack and get the initial velocity. We know our acceleration on our planet. We know the acceleration on other planet. we know acceleration of Earth, we know acceleration of gravity on the other planet. What we don't know is the initial velocity. You see, if you throw a rock on Earth, or you throw a rock, let's assume as hard as you can. Throw as hard as you can here, or as hard as you can on the planet, you should have the same initial velocity, but the way that acceleration is going to affect it is different. So you're still standing on the ground, you're still throwing the rock. So here's what we're going to do. The idea behind this problem is use what you know about Earth to figure out an initial velocity. Take that initial velocity, modify what you know about this planet. So this planet, this is acceleration on this planet. You don't have to figure that out again. You are going to have an initial starting point of 0, not 20. So you're going to be on the ground, but you're also going to have an initial velocity. So all we need to do is augment this with initial velocity and lack of any other height, and we're going to be fine. Let's figure out this initial velocity that you can throw your rock. That starts with on Earth. So on Earth, your acceleration is negative 32 feet per second squared. I hope that at this point you're really okay with why we're using feet per second when dealing with this situation. Our initial velocity, that's what we're looking for. Our initial position, you're assuming you're on the ground. So we're going to assume your height is negligible. You're just throwing it up there. We're assuming you're on ground level there. So let's start with our integrals. We know that velocity is an integral of acceleration. Initial velocity, man, we don't know. But we do know something. We know that at the maximum height of 144 feet, what's our velocity going to be? Velocity is going to be 0. So maybe we write this down. At the maximum height, at 144 feet, velocity equals 0. When does that happen? At 144 feet, our velocity is going to equal 0. Our velocity is going to equal 0. So when we get down to it, our c sub 1 is negative 32t. That's cool. So we're going to be able to use that a little bit later. So we know that our velocity is negative 32t plus c1. At 144 feet, we've reached our max. Our velocity will be 0 at that height. That we can use to say, hey, c sub 1 is negative 32 feet. Now, we can't... Yeah, I did it again. It is positive 32t. We can't really plug that in here. It's going to give us 0. Yeah, it is, because that's our starting velocity. That's what that says. Like if you plug that in right now, you'd have your starting velocity of 0. So let's go on. Let's do our position. So take an integral of velocity. We always get our position from that, and this is going to be negative 16t squared, that's starting to look pretty familiar, plus c1t plus c2, another arbitrary constant. But this one we do know. We do know our initial starting spot. We're on the ground, and we're throwing this up, so we're assuming that our height is 0 here. So if t equals 0, we get a height of 0. 0, 0, 0. C sub 2 is going to be 0. Here's what else we know. This is where this comes in. At 144 feet with a velocity of 0, we have c sub 1 equals 32t. So if we put our position, our height of 144, we can substitute c sub 1 equals 32t. Let's do that now. So height of 144 feet. When does that occur? So how long does it take for that to happen? C sub 1 is 32t. I wonder if you could do it different. I wonder if you could solve that for t and find C sub 1. I bet you could. I'll do it a different way in just a minute. So this is all going to give you 16t squared. And if we do that, that's got to be 3. So you can backtrack now. So you know that you achieve your maximum height of 144 feet in 3 seconds. Since you had this solved for C sub 1, that's 32 times t. Plug your 3 in. You know that C sub 1 is 96 feet per second. C sub 1 is 96 feet per second. So C sub 1, remember what C sub 1 is. C sub 1 is also your initial velocity. So we know right now that on this situation, if you were going to throw a rock 144 feet in the air from a starting spot of 0, you had an initial velocity of 96 feet per second. That's pretty cool. It's going to take you 3 seconds for you to throw the rock. 1, 2, 3, reaches 144. The velocity is now 0. You had to have launched it at 96 feet per second. Does that make sense to you? I hope that makes sense to you. So we're using our knowledge of Earth's gravity. We know that we don't have initial velocity. That's literally the only thing we're looking for. We have an initial position. We take our integral. We know that at 144 feet, our velocity is 0. Well, you can solve for C sub 1. Cool, we did. So we have C sub 1 is 32t. We wait for position, just like before. We know that our position of 144 feet allows us to substitute in C sub 1 equals 32t. Then we're able to solve for, hey, 3 seconds. It takes 3 seconds for us to reach 144 feet, and our initial velocity had to be 96 feet per second. I mentioned also that you probably could do this a different way. I think you can. So if we solve for t, so add 32t on one side and then divide by 32. Right down here, from this spot, you should be able to plug in C sub 1 over 32 and C sub 1 over 32. As your t. And so what that would give us, here's C sub 1 squared, here's C sub 1 squared, here's 32 times 32, and here's 32, so let's see, 16, can't really do it that way. I don't know, try it, see if you get 96, I'm guessing you probably do. In fact, you could probably plug it in right now, say what's 96 divided by 32, so that would be 3. 3 times 96, 3 squared 9. But that's 288. Yep, 28. So this would be, if you plug in 96 here, just to check to make sure it works, if you plug in 96 here, here, and here, you get negative 144 plus 288, that's 144. So it does work. And if you proceed to do it from here, you will get C sub 1 equals 96. So either way, I've done it this way in the past, it's just the numbers work out, they're harder to deal with. So I showed you 2 ways here. Take one of them, it doesn't matter which one you do. You're gonna get either t equals 3 first and then backtrack to 96, or using this method with solving for t, this will give you C sub 1 equals 96. Either way, you've just found your initial velocity. You're throwing that rock up there at 96 feet per second. Now let's go on to the different planet. So knowing that we have 96 feet per second, that's all we really need. our initial velocity is 96 feet per second. Just notice what we ended with over here. We know that the position function for this new planet, whatever it is, it's just -5 t squared plus whatever your initial velocity is, t, plus whatever your position is, x sub 0. But we know that. We know that if you're throwing something up from the ground, this is 0, and we just found that. So our position function, we just augment this. We know that the acceleration is based on -10 feet per second squared. So when we plug it into a position, it's -5, and cut it in half, plus 96t. Now that we know our initial velocity, that's pretty neat. So we move on, and we say, how high could you throw that on that planet? Well, what's your velocity? What's your velocity on that planet? Come back over here. Our velocity is right here. So our velocity is just c sub 1 t. Well, I guess it's not. We have to augment that, don't we? Plus your 96 feet per second. So you could do that. You could also be smart about it and say, Leonard, dude, velocity is always the first derivative of position. Take a derivative, -10t plus 96. Oh my gosh, it actually works. When will you hit a maximum height? You hit it when your velocity is 0. So if we set our velocity equal to 0, we're going to figure out when we achieve that maximum height. Velocity 0 equals -10 plus 96, add 10t, divide by 10, you get 9.6 seconds. So we are going to hit our maximum height after 9.6 seconds. Here, look at Earth. Earth was 3 seconds. 3 seconds we hit our maximum height. That's why I did it that way first, so you see the time difference. Why the difference? Gravity is much less here. So on Earth you go 1, 2, 3. You just hit the peak. Here you throw the same exact hardness, whatever. You get 9.6 seconds, then it's hit its peak. This is going to be much higher. So, yeah, we had initial velocity. We came back over here. We said this is what our acceleration is. Let's see where I lost it. This is what our acceleration is. This is what our position is from a height of 20 feet. Let's make a difference. Let's make it from 0 feet. Okay, well there's no initial position that's gone. It's the height of 0. We also have an initial velocity of 96. Look, we can come back here and say, hey, initial velocity is 96, not 0 anymore. That changes our initial position, that changes our velocity functions. But now we say, how high does something go? Well, it's going to reach a height when its velocity is 0. That's 9.6 seconds. Plug this back into your position. And we get about 460.8 feet. Man, I'm really hoping this is making sense. I'm hoping that you understand that once you have acceleration, you're good to go. You just do some integrals. Once you have initial velocity, you're even better. So you can solve a lot of these things by just understanding how the formulas work. And if you need to change initial velocity, fine, just add it. That's okay. Or just add it with a t here for your position. So I would try these again. Make sure you're going through these a couple of times. I think that's about it. Yeah, I think that's about all we do. I said 10. We went through 9. The rest of them are very, very similar. I don't want to really waste your time. I was going through and going, man, these are really, really the same. So the main ideas for all of these examples are start with your acceleration and take an integral. That's going to give you velocity plus a constant. Use your initial velocity to change that arbitrary constant. Take another integral for position. Use your initial position to modify that position function. If you can do that, that's a straightforward example. If you have an acceleration that you don't know, you are going to have to find the position function typically to solve that. If you want to find the maximum height, find out when the velocity is 0. However long that takes is however long it takes for you to achieve that maximum height. We use that a lot. Once you find an initial velocity, or if you need to find an initial velocity somewhere, so like this, you can go ahead and modify the formulas that you have from other situations to make that work for you. So that's about it. We've done a ton of examples. I'm tired. You're probably tired of watching me do this stuff, but I hope they were useful for you. I know we spent over an hour doing this, and that's a lot of examples, but because these can take many different shapes and forms, I wanted to give you that the abundance of just hardcore math worked out. So I hope it helped. If it did, please let me know that was helpful. I appreciate it. You guys have a good day. Hopefully your studying's going well, and I'm going to come back with slope fields in a while. All right.